Okay, we've done circular motion, and now we're going to do Newton's law of universal gravitation, which is directly related to uniform circular motion, but we're now looking at objects on a larger scale. So this will be applicable to really any objects that have mass, but a lot of these problems are going to be done out in space or a little bit more abstractly. So let's just get right into what Newton's law of universal gravitation is. It's going to state that any two objects attract each other with a gravitational force proportional to the product of their masses and inversely proportional to the square of the distance between them. And the force acts in the direction of the line connecting the centers of the masses. So in the lab, the simulation that we had done, you had the two objects, you changed their masses, and what you measured was the distance between the centers of those masses. So what that's telling us is that any two objects, so let's say you've got an object here and an object over here, the force is going to act in the direction of the line connecting the centers of the masses. So assume there's an invisible line here. I know that's not very great. So an invisible line here. You're going to have the gravitational force acting in this direction. So towards the center of, I guess their center of mass as they're rotating each other. As long as something has a mass, it's going to have a gravitational force. So everything is attracted to everything else by this force of gravity. And this is not to be confused with weight, it's just a gravitational attraction. Okay, the equation for the force of gravitational attraction. We kind of touched on this with the lab. G, and this is a big G, not a little g, equals G m1 m2 over r squared. And I'm going to define what everything right here is. So we've got Fg, which is the force of gravitational attraction. And we do want to use the capital G for here. The radius is the distance between the centers. This is important. The centers of the two masses. M1 and M2 are your mass. And this G right here is the universal gravitation constant. So Fg equals G m1 m2 over r squared. When you did the computer simulation, some of you got that there was a direct relationship between force and gravity. Some of you got that the force and the masses were a square relationship. And that depended on what you did for your variable. So if you used the same mass and just increased, so in other words, if you had used the same number for both of the masses and increased that, you probably saw that it was a square relationship. That would make sense, because 10 times 10 is 100 units would be kilograms squared. If you only varied one of the masses, you would have seen that there was just a direct linear relationship between force and the mass. So force is directly proportional to the mass unless you have the same mass, in which case it's a square relationship. Force is inversely proportional to the square of the distance. So I think everyone got that same thing. You had to linearize the lab twice, where you were doing 1 over the distance and then squaring the distance. And this is written very poorly. This should be r squared. I'm glad I caught that now. So this should be r squared. Okay, fix that. Sorry about that. So an inverse square relationship for the distance, a direct relationship for the mass, unless your masses are equal, in which case that would be squared. So that's why for the lab, some of you had gotten a squared relationship. So this is the equation for the universal gravitation, force of gravitation between two objects. F equals G m1 m2 over r squared. And it does not matter what you make m1 or m2. What is the universal gravitation constant? This is a good number to store in your calculator. G equals 6.673 times 10 to the negative 11th. The units are newtons, meters squared, per kilogram squared. You want to store this in your calculator as G, so just type in 6.673 E negative 11 STOG. You'll use this number a lot every time we do these kinds of problems, so you want to make sure that it's just easy enough to recall in your calculator. So looking at these units, newtons, meters squared, per kilogram squared, just to see how they all work out. In the equation, FG equals G M1 M2 over R squared. Let's just look and see how these units work out. The units for G, newtons meters squared per kilogram squared. Mass are both in kilograms, and the radius is in meters squared because it's squared. So that gives us, for G, newtons meters squared per kilogram squared times kilograms squared over meters squared. Those all cancel, and you're left with units of newtons. So, force of gravity, force of gravitational attraction, reduces to units of newtons. That's why this is such a big mess. But what you do need to know, and this I think is also on the equation sheet, is this number. Again, it's easiest to store it in your calculator. Universal gravitation is known as an inverse square law, so that means something half as far away will have 4 times the gravitational force, something twice as far away will have 1/4 the gravitational force. The reason why. So inverse square law means that it's proportional to 1 over the distance squared. So if something is half as far away, so this is 1 over 1/2 squared. This is 1 over 1 over 4. Your force of gravity is 4 times. If it's twice as far, so this is 1 over 2 squared, your force of gravity is 1/4 as much. So that's how that works. In other words, the farther away something is, the weaker the gravitational force. That's going to make sense. The closer you are, the stronger the gravitational force, so just think of it logically that way. But know that it's a square, so it's an inverse square relationship. It's not inverse. The more mass something has, the more gravitational force it's going to have. You're a lot more attracted to the Earth than you are to the person sitting next to you, because the Earth is a lot more massive than whoever's next to you. So that's why force and mass are directly proportional. Force and distance are inversely proportional. Okay, some helpful constants that you might want to also store in your calculator. The mass of the Earth, we're going to call that a capital M, and this is equal to 5.98, that's a decimal, times 10 to the 24th kilograms. So I would store that in your calculator as M. And then the radius of the Earth, I'm going to call this a capital R, store this in your calculator as R, equals 6.38 times 10 to the 6th meters. So you will also be given those if you ever need them on a test or a quiz, but these are helpful to have stored into your calculator as well. Okay, so let's skip to the examples. First example tells us to determine the force of gravitational attraction between the Earth and a 70-kilogram physics student if the student is in an airplane at 10,000 meters above the Earth's surface. So what we have here, here's the Earth's surface. They're in a plane. Obviously, this is not drawn to scale. And they're flying around the Earth. Our given information. Mass is 70 kilograms. They are 10,000 meters above the Earth's surface. So I'm going to call that height. Height is 10,000 meters. And we're looking for force of gravitational attraction, so that's F big G. You don't necessarily need force diagrams for these. you're looking for the force between the Earth and the student. So they're equal but opposite forces pointing towards each other. So if that's the student, this is for the Earth. Those are equal arrows, they're just pointing in opposite directions. It tells us that they're 10,000 meters above the Earth's surface. If you recall from the first slide, your distance is measured from center to center. So we're looking from the center of the Earth to the center of the student who's in the airplane. That's why I use this term height, because that's referring to how far above the surface of the Earth that student is. Which means that your total radius would be equal to the radius of the Earth, and you'll notice that I always just write this as capital R, would be the radius of the Earth plus the height. So FG equals G M1 M2 over R squared. Again, my radius is equal to the radius of the Earth plus the height. FG equals G M1 M2 over R plus H squared. For the mass, if you're dealing with the Earth, it doesn't matter if you make M1 or M2 the mass of the Earth. Again, you will find that I just use a capital M if I'm dealing with Earth. So FG equals GM M2 over R plus H squared. This mass of the student could be either M1 or M2. In this case, it's M2. We know the height, the mass, and the radius of the Earth are givens, as is the big G. So let's put these numbers in. FG equals GM. Again, you'll find me just using the letters G, M, and R if we're dealing with the mass or the radius of the Earth, because there's no need to write them all out if they're stored in your calculator. So this is GM times the mass of the student, 70 kilograms, divided by the radius. And again, the radius is the distance between the centers. So this is the radius of the Earth plus the height above the Earth's surface, so R plus 10,000 meters. And that number is squared. The biggest mistake I see here is forgetting to square right here. So a lot of times you'll be fine with the top, but it's forgetting to square this bottom number. So in your calculator, if you stored the numbers like I told you, you would just hit alpha G, alpha M, 70, hit enter, divided by the radius of the Earth, so R, so 6.6, what was that? 6.38 times 10 to the 6 meters plus 10,000 meters, parentheses, squared. And we should get 684.09, keeps on going. Remember, these units will reduce to newtons. Only one sig fig. So the force of gravitational attraction between the student in the plane and the center of the Earth is approximately 700 newtons. And the trick here again was this radius. So making sure that your distance was between center to center. So for the center of the Earth, you have to account for the radius of the Earth itself. Let's do one more example. It tells us if the ISS, or the International Space Station, is orbiting at an altitude of 450 kilometers above the Earth's surface, what would be the orbital speed of the ISS, and what about the period? So here we've got Earth, and we've got the International Space Station orbiting around the Earth. Given. It tells us that it's 450 kilometers above Earth's surface, so that's the height. Height is equal to 450 kilometers, which is 450,000 meters. We always want to make sure we're in meters because G, again, has units of newtons, kilograms squared per meter squared. So these both have to be in meters. Let's see, it wants to know, that's all we're really given. It wants to know what the orbital speed is, so we're looking for speed, and then we're looking for period. And given one, we can easily find the other. We already know what the radius of the Earth is. We already know what the mass of the Earth is, so I'm not going to write those in as givens. Let's start with this equation. Fg equals g m1 m2 over r squared. So this will tell us the force of gravitational attraction as the satellite is orbiting the Earth. But, so let's see, the way I drew my force diagram, this is the direction of the gravitational force. But the ISS is traveling in a circle, and the center of the circle is in the same direction as this force of gravitational attraction. So that means that my gravitational force must also be equal to my centripetal force, which means that G m1 m2 over r squared must also equal my centripetal force, which is mv squared over the radius. Reason being, again, is because there's only one force acting on the ISS. It's moving in a circle. Therefore, that force must be equal to the centripetal force as well. Looking at these masses, this is the centripetal force for the satellite, which means that this mass is the same as one of your two masses. Your mass of the object will end up canceling out. So that goes away. I'm just going to call this m1 over here. So to avoid confusion, let's make m2 equal the mass of the Earth. This radius goes away. You're left with 1 here. So this leaves us with g m2 over r equaling v squared. So just rewriting this, v squared equals g m2 over r. m2 is the mass of the Earth, and this will be true for any universal gravitation problem where we're throwing in centripetal force. The mass is the mass of the more massive object. So it's the more massive object, it's what's being orbited. So it's whatever the object is going around. So what's being orbited, not the object that's doing the orbiting. So in the case of the Earth, v squared equals gm over the distance between the two centers. It tells us that the ISS is 450 kilometers above. So remember from our last problem, the radius will be equal to the center of the Earth, so the center of the Earth to the surface, the radius of the Earth, plus the height. So the radius will equal the radius of the Earth plus 450,000 meters. So speed squared equals gm over r plus 450,000 meters. If you stored this in your calculator as gm and r, again, this becomes a pretty simple equation. So alpha g, alpha m, hit enter, divided by our radius plus 450,000 meters. V squared equals, this is a big number, 584,25387.99 meters squared per second squared. Taking the square root of that for our speed, you should get 7643.65, keeps on going, meters per second. There should be no squared here. So how fast is the ISS orbiting? With 2 sig figs, this is going about 7,700 meters per second. That's pretty darn fast. The next question it asks us is, what is the orbital period? Well, we know that the only equation with period is v equals 2 pi r over t. So t equals 2 pi r over v. So period equals 2 pi times the radius. Again, this is the radius of the Earth plus 450,000 meters divided by the unrounded speed we just found, 7643.65, keeps on going, meters per second. So period equals 5614.65 0.35 keeps on going seconds. 2 sig figs, the period is about 5,600 seconds. And if you divide that by 3,600, you're going to get it's about an hour and a half-ish. So it takes around 90 minutes for the ISS to orbit the Earth. Again, going at the incredibly fast speed of 7,700 meters per second, it's pretty believable that it can go around in an hour and a half. So this is how we solve gravitation problems. Again, what I did for this one was set the gravitational attraction force equal to the centripetal force. Because the ISS is in a circular orbit, the gravitational force is directed towards the center of that circle, so therefore that equals the centripetal force. From there, it just became pretty much a centripetal force equation, looking for the orbital speed. And yes, it will always be true that orbital speed equals gm over r. Orbital speed squared equals gm over r. You could also write this as v equals the square root of gm over r. And this should be a lowercase r because it's not always the radius of the Earth. But this mass is always the mass of whatever's being orbited. This radius is just the distance between the centers. So this is what you can always use for orbital speed. And once you have speed, you can very easily find period.